Hello, my dear students, and welcome back. I know your board exams are just around the corner, and sometimes this chapter can feel a little scary. But don't you worry, by the end of this session, you'll see how simple it is, and you'll be ready to get full marks. Let's get started. So, are you ready to dive in? This chapter is actually one of my favorites because it's all about simple logic and patterns. We're going to break it down step by step, and you'll see just how easy it is. Our mission? Full marks, nothing less. Let's do this together. Okay, let's begin. You know, the entire story of this chapter revolves around just one family. And the head of this family, the superstar, is the carbonyl group. So first, let's meet its three most important children.
Now, just look at this. Our hero is so simple. It's just a carbon atom with two hands held up, sharing a double bond with an oxygen atom. That's it. This little group, the C double bond O, is the functional group that defines every single thing we will talk about today. Simple, right?
So, what the carbonyl carbon holds in its two hands, that decides everything. If one of those hands is holding a hydrogen atom, we call it an aldehyde. If both hands are busy holding other carbon groups, it's a ketone. And if one hand holds a hydroxyl group, an OH, it becomes a carboxylic acid. See? It's all about who's attached to that main carbon.
Now that we've met the family members, let's learn how to call them by their proper names. Don't worry, it's not complicated at all. It's actually a very simple game of changing the ending of the name.
Look how easy this is. For aldehydes, you take the name of the parent alkane, like ethane. You chop off the E at the end and you stick on -ol. So ethane becomes ethanol. Simple. For ketones, you do the same thing, but you add -one. So propane becomes propanone. And always remember that carbonyl carbon is the VIP of the chain. It always gets the lowest possible number.
Okay, bachcho, time for a quick test. This type of question is a favorite for the examiners, pakka. Look at the structure carefully. 4 carbons, a double bond, and an aldehyde group. What do you think its name is? I'll give you a moment to think about it.
And the answer is but-2-enol. I am sure most of you got it right. But, because there are 4 carbons, 2-ene, because the double bond starts at the second carbon, and al, because it's an aldehyde. Put it all together, but-2-enol. Shabash, well done.
So, now we can name them. But how are they made? Let's look at how to prepare them. We will only focus on the VVIP reactions, the ones that are almost guaranteed to show up in your exam paper.
First up is the super famous Rosenmund reduction. Think about like a recipe. You start with something called an acyl chloride, then you add the magic ingredient, hydrogen with a special catalyst. Now the barium sulfate here is very important. It acts like a brake. It poisons the catalyst a little so it doesn't get overexcited and reduce the aldehyde all the way to an alcohol. We want to stop at the aldehyde, and this helps us do just that.
And here is the full reaction. Please, my dear students, write this down, practice it. This is a pakka 3-mark question, I'm telling you. The main thing to remember is acyl chloride plus this special catalyst gives you an aldehyde.
Okay, next up is another VVIP reaction, the Stevin reaction. This one is also very easy. We start with a nitrile, which has a carbon-nitrogen triple bond. The reaction first turns it into an intermediate called an imine. And then you just add some water, and ta-da, you get your aldehyde. So just remember the journey. Nitrile to imine to aldehyde. That's the Stevin reaction for you. All right, now we are at the real core of the chapter. Understanding these next few ideas is the key to locking in those marks. We're going to look at what these compounds do, their properties, and how to tell them apart. So let's start with a very important conceptual question. Both aldehydes and ketones have that same carbonyl group, right? But for some reason, aldehydes are always much more reactive. Why is that? What makes the aldehyde the more, let's say, hyperactive child of the family? Well, there are 2 main reasons for this. First one is steric reasons. That's just a fancy word for crowding. Imagine an aldehyde has a tiny little hydrogen atom, so the path to attack the carbon is wide open. But a ketone has 2 bulky carbon groups, like 2 big bodyguards blocking the way. It's much harder to get through. The second reason is electronic. Those 2 groups on a ketone donate electrons, making the carbonyl carbon less positive. If it's less positive, it's less attractive to an attacker. So aldehydes are more reactive because they are less crowded and have a more positive carbon. So,
If I give you two test tubes in the lab with no labels, one with an aldehyde and one with a ketone, how would you find out which is which? It's time to play detective, and lucky for us, we have some very simple chemical tests to solve the mystery.
So we have two master detective tools, the Tollens test and the Fehling's test. And here is the big secret. Both of these tests give a positive result only with aldehydes. Why? Because aldehydes are easy to oxidize, but ketones are not. With Tollens reagent, an aldehyde gives a beautiful silver mirror. With Fehling's reagent, you get a red-brown solid. And the ketones? They do nothing. They just sit there and watch the show.
I'm absolutely sure you have all seen this on YouTube Shorts or Instagram Reels, that magical video where a clear liquid suddenly forms a perfect, shiny mirror inside a test tube. Well, that is this exact same Tollens test. It's one of the most beautiful reactions in chemistry, and it's our best friend for identifying aldehydes.
Now for another classic exam question. This one can be a little tricky, but we will make it very simple. Your exam paper just loves to ask this. Why are carboxylic acids stronger acids than phenols, even though the phenoxide ion seems more stable because it has more resonance structures?
The key here, my dear students, is about the quality of the resonance, not just the quantity. In the carboxylate ion, after it gives away a proton, the negative charge is shared equally between two highly electronegative oxygen atoms. Oxygen is an expert at handling negative charge, so this is very, very stable. But in the phenoxide ion, the charge is spread out over one oxygen and the less electronegative carbon atoms. Carbon is not so good at this job. So the carboxylate ion is much more stable. And the golden rule is, the more stable the conjugate base, the stronger the acid. That's why carboxylic acids win.
All right, everyone, deep breath. Let's do a super quick, rapid-fire revision of all the key points. This is your last-minute checklist to make sure you have everything you need for full marks. Are you ready? Remember these 5 golden points. 1. The hero is the carbonyl group, C-double-bond-O. 2. Naming is easy. Aldehydes end in -al, ketones in 1. 3. Rosenmund and Stephen are your VVIP reactions for making aldehydes. 4. Tollens test means silver mirror for aldehydes. And 5. Fehling's test means red precipitate for aldehydes. Master these 5 points and you have mastered this chapter.
And before we finish, just a little something to think about for you, my future toppers. Chemistry is not just in your textbooks, it's all around you. Can you think of an aldehyde or a ketone that you use every day? What about the acetone in nail polish remover? That's a ketone. Or the beautiful smell of dalchini or cinnamon? That comes from an aldehyde. Think about it.
And that's all for today. You have done a great job. I just know you are going to do wonderfully in your exams. If you found this session helpful, please don't forget to like, share it with your friends, and subscribe to the channel. And if you have any questions at all, just leave them in the comments below. All the very best.